Okay, good afternoon, everyone. After the previous wonderful session, we have now four more speakers who will be talking about different aspects of energy system modeling. So, the first speaker we have today is Dr. Neha Mehta, who is an assistant professor at the University of Birmingham in UK. She will be talking about overall system level modeling. So, since we have less time in this session, and I don't want you to wait for your lunch quite long. So, what we are doing, we are keeping every talk for about 10 minutes, and we'll take one or two questions depending on time. And I have also cut short the bio of all the speakers, so I hope they don't mind, because you just Google their name, they are famous people, you will find a lot of information about them. So please, Neha, stage is yours.
So I'm Neha Mehta from University of Birmingham, and I will be talking about decarbonization through heat pumps or using heat pumps, and how they are related with um, greenhouse gas emissions potential. And I think it was very wonderful. Just the talk before this mentioned heat pumps, and I quite like it. Thank you. At the fourth point where you mentioned electrification was good introduction to this session. Very good. Thank you. So before I begin, I want to say that it's really an honor for me to be here. When I was at airport struggling with the flight, someone said to me, "Sister, why are you making a fuss? Everyone is here standing in the queue and their families are waiting for them. Why should we give you a seat rather than them?" And at that point, I really didn't have an answer. And I was wondering, it did take me a moment to reply, either you give me a flight now or I'm going home. I won't go and travel to Chennai if you give me 8 December. So this is how much for every one of us the Energy Summit means. I hope you would have seen with all the panicky emails by now. I also want to thank two master's students who did most of the research for this presentation, and they were co-supervised by me and supervised by Jonathan here. So let's get to the background. Heating and cooling is something that not many people are talking about. We do talk about electrification a lot, EVs a lot, green hydrogen a lot. I mean, we got a panel on green hydrogen. Heating and cooling accounts for 50% of the global energy consumption. And more than 40% of the global carbon dioxide emissions are from heating and cooling. If you look at the International Renewable Energy Agency's predictions, from 2016 levels to 2050, the demand for cooling is going to be increasing by 45%. A lot push is going on heating and cooling, and the major reason is that people need comfort in their homes. We can't forget energy at homes. What kind of inverters you are using, what kind of inverters I am using, what kind of energy source I have at my home plays a really big role, though we don't realize, we only look at it in bills, but it does play a big role in carbon emissions. About 1/3 of the population which needs cooling is currently doesn't have the cooling devices. The people in the hot climates will be going for more air conditioners or more cooling systems, which means we should be talking about heating and cooling and how space or domestic demand is met. While because I'm based in University of Birmingham, my today's focus has been more about UK. And in the UK, about 25% of GHG emissions are from domestic heating. And one way, as the previous talk mentioned, is maybe let's shift to electrification more and shift from gas boilers to heat pumps to reduce the need for natural gas and therefore the potential greenhouse gas emissions. It's also important not just because of greenhouse gas emissions, but also because of energy security. You can, if your own renewable source productions are doing well, then you won't need natural gas to be imported from somewhere else. However, we also know that the heat pumps or the environmental sustainability aspects of heat pumps are interlinked with electricity grid characteristics, ambient temperature, amount of lift provided by heat pumps, and the type of heat pumps. And we also know from research conducted mostly from 2015 to now that about 80 to 85% of GHG emissions or global warming potential or climate change potential because of heat pumps happens during, or even the natural gas boilers happens during the use phase or the operation phase. And the major reason is if you have a product which works for 20 years but is using energy all over the 20 years, then of course that energy demand is going to be playing a big role in it. If you look at these graphs, they are from studies published in 2015 to 2021 or 2023, sorry. And the variation of global warming potential goes from almost 100 to 500. And the reason was different geographies of placement, different geographies of deployment of those heat pumps, and how those heat pumps will have different electricity grid characteristics as well. And therefore, we need more place-based action when we talk about climate change. When we talk about reducing greenhouse gas emissions, we should take more community approach. I do agree with that. We need to take more local approach. Yes, we should be meeting global targets, we should be meeting national targets, but we shouldn't forget about the communities. So the aim of this whole project that we had master's students helping us was to just see how air source heat pumps deployment will take place in the UK and how much greenhouse gas emissions would be related to that. And why we thought that was important to understand was because if you see UK or most of Great Britain, from southwest of England to Scotland, the variation in electricity grid is very high. Gram CO2 per kilowatt hour is very different from south to the north. More because, well, wind doesn't blow everywhere and sun is mostly not everywhere in the UK. So we use the data sets on hourly weather data from NASA Mehta 2 and use ArcGIS to convert that on R and R level for the whole year of 2022. Another data set we used was local energy performance certificate data, which actually gives you the type of dwelling in a local authority. So if you say local authority is more like district here, sort of that comparison, yeah. So if you see on a local authority level, we do have data on what kind of dwellings we have. Are those terraced houses, semi-detached houses, detached houses, flats, different dwellings and their floor area, which means we can also see how much is the total floor area in a local authority. If you see London is crowded, Greater London is really crowded, probably more than 2 or 3 times than every other local authority. We also had National Grid ESO dataset, which gives you R on R variation in the electricity grid carbon intensity, and it's readily available. If you see just today, you go on National Grid ESO, it will give you just at 6:25 a.m. this was the gram CO2 per kilowatt hours and how much was the percentage of renewables as well. So about 60% was this morning. So now let's talk about the calculation flow chart. And so all dwelling floor area can be converted to heating demand if you use a comfort temperature of 21.2 degrees centigrade and see the difference between ambient temperature and the heating demand and use the thermal potential of the homes, which can be converted to gas demand because you can assume that boilers would have about 84% efficiency. And that hourly temperature can give you COP of heat pumps. Most heat pumps will have a COP or coefficient of performance linked to them. Most air source can go 2 to 4, more like, and geothermal can go 3 to 5. Geothermal perform better than air source heat pumps because the ground temperature is much more constant or much less variable compared to the ambient temperature. This COP of heat pumps can be converted to electricity demand because now we know that the COP is about 2 to 3, and which leads to CO2 emissions. These are some results on floor area. What are the floor area in England, Scotland and Wales, and the number of regions and their average carbon intensity. And we also use the fact that not all heat pumps will have COP, as in like COP of heat pumps is measured in the factory, which can be different from performance at homes. We also accounted for that. And our findings showed that the annual heating demand that we performed was about 320 terawatt hours for this study, which is very much in line with other models that have been used in the UK. We also ranked our findings and found out the percentage reduction in GHG emissions in different regions, and they varied from 50.4 to 95. Now I should mention Northern Ireland is not ranked here. The only reason is that Northern Ireland has different grid compared to rest of the UK, so we didn't perform the data analysis on that just yet. And if you see in Great Britain, Scotland and Northeast England has the highest percentage reduction in carbon emissions, while Wales has the lowest. The main reason for that was the carbon intensity of the electricity. And coefficient of performance also varied, and Southwest England had the slightly higher than the other regions in England. So what are the next steps? I did ask for a place-based approach, which means that we should not be just looking at regions, but actually local authority level. So we are currently doing calculations on local authority level, and also considering that the fact that heat pumps won't be switched on for the whole day. They would be more like in the time you are actually in the home, not 9 to 5, no one would be at the home to actually use the heat pumps. So that time the heat demand would be really less compared to the evening time or the early morning hours. We do, or not just we, everyone realizes that environmental sustainability goes beyond GHG savings. And this is where I should do a shameless promotion of the project. It's about barocaloric heat pumps. So we would be looking at how barocaloric heat pumps would be deployed, not just UK, but globally, and how those solid state materials can be replacing refrigerants to not just work on CO2 emissions, but also ozone layer depletion, terrestrial acidification, other categories of environmental sustainability. And the last one, which we should never forget, is heat pumps. And like every other device, electric vehicles, natural gas boilers, everything is part of a much wider system. The deployment would be much influenced by the co-location of the current infrastructure and the future infrastructure demand. It will be influenced by, yes, consumer behavior. It will be influenced by fuel poverty and many other aspects. And these are some of the references that I used for the calculation, and thank you.
Any quick question? So I can ask a question. So for the benefit of the some of the audience member may not be aware of what the heat pump is. So can you maybe in simple terms explain what a heat pump is?
So heat pumps do not generate heat, but they actually transfer heat. So if you have heat pumps outside your home, they will use the ambient air temperature, and there would be a refrigerant connected to it or a cooling liquid, which was the same in yesterday's project. They had refrigerant system. The refrigerant takes on the heat from the system, compresses, evaporates, and then transfer the heat inside the home. This is the simplest, very, very quick one. Yeah, that's the most important thing. It can work in reverse, which means ACs can be replaced by heat pumps.
Same heat pump can do both functions.
Yeah.
Great. Thanks.
It's
Neha.
like refrigerator. So
Okay.
if you reverse the refrigerator, that's how heat pumps work in heating mode.
Thank you, Neha.